Hi there. Over the last few videos we've been looking at Runge-Kutta method, and this is all about evaluating the function on multiple points within the time step. And we've seen that this can be understood and analysed in terms of the underlying Taylor series associated with the method. And today we're going to finish off the Runge-Kutta with the fourth order Runge-Kutta method, just showing you how that's structured. And then we're going to look at the other most common type of method that involves multiple function evaluations, the so-called multi-step methods or Adams methods, after the person or one of the persons who invented it. And this contrasts with the Runge-Kutta method in that it evaluates the function on the time steps rather than within the time steps. And it can be derived by approximating the function with a polynomial on the right side. Okay, so I'll hand over to the board. Okay, moving over to the board. So now we've considered second order Runge-Kutta. Now we're going to just consider what fourth order Runge-Kutta looks like. Partly because this is a very commonly used routine in many applications where we have nonlinear ordinary differential equations. So with RK2 there were two function evaluations. Within the time step. So by analogy, with RK4, there are four function evaluations. So there's a trade-off here, really. We're going for fourth order accuracy. RK4 means fourth order accuracy, RK2 means second order. So to get that extra order accuracy, we have to increase the number of function evaluations. And you can derive the RK4 scheme from Taylor series in the same way, and as I said before, we're not going to go into that because really it doesn't add any new principles. And but if you're interested, there are papers out there that derive the fourth order from first order, but I'm just going to show you what it looks like. So for RK4 we now have, where in RK2 we had two coefficients, we now have four evaluations. And sometimes this is then referred to as stages. You've got stage 1, stage 2, and then so called down to stage 4. So another name for the RK type schemes, Runge-Kutta schemes, is sometimes called a multi-stage scheme, because you have multiple stages, multiple function evaluations. So K1 again is our function right at the start of the time step. And let's just do what K4 is. Oh no, do that in a minute. Let's do K2. Is an evaluation kind of in the middle. Looks a little bit like the midpoint algorithm. In fact, this stage is like the midpoint algorithm. Then there's another evaluation somewhere in the middle, but what we're doing each time is we're using the previous stage to update it. So the sort of kind of roughly midpoint for K2 uses K1, then K3 uses K2, so you have delta T onto K2, Tm plus delta T on 2. And then finally K4 uses K3 plus delta T to K3, Tm plus delta T. Okay, so it's sort of a sequential multi-stage scheme. You have K1, use K1 to evaluate function somewhere in the middle, then use K2 to evaluate another function in the middle, then use K3 to evaluate a function somewhere at the end, because we've got delta T on 2 there. And then the final step is then a weighting of those four function evaluations. And this is fourth order accurate. And as I said, this is commonly used when I come to do like nonlinear equations, like the Lorentz equation in term 2. We will be using this Runge-Kutta 4, fourth order. Okay, so that's the end of the Runge-Kutta method, sometimes called multi-stage schemes. And what you're trying to do is evaluate the function within the time step. So RK schemes evaluate f within or at the end of the time step. The next one we're going to look at, in fact this is the final ordinary differential equation method for time stepping, is called a not the step method, it's called a alternative is multi-step method rather opposed to multi-stage. And the key idea with this is f is evaluated on the time steps. Let's do a timeline again. You've got Tn there, Tm plus delta T, and you have Tm minus 1, maybe Tm minus 2. Now the RK schemes, remember, is we're often using the function, say, let's use the RK4 in its example. Evaluate within that time step or right at the end. The idea with the multi-step ones though is that we think it's a bit of a disadvantage sometimes to, and it causes extra computational effort, if you like, to calculate the function within there. But an alternative is to actually evaluate it directly on the time step, maybe even Tn minus 2, and that would be a multi-step. So both are trying to do a better job of evaluating or of integrating the function f on the right hand side. Both involve leaving the left hand side alone, really, using xn plus 1 and xn, but they increase in value. But both have different advantages. Some use the values on the time step, and other ones are called multi-step. The RK schemes don't. And multi-step schemes often are called Adams something schemes. They're either Adams Bashforth or Adams Moulton, but they're Adams something schemes. And that's what we're going to talk about next. So the underlying theory between of the Runge-Kutta schemes was that there was a Taylor series that you expand to a certain order of accuracy, and you derive the scheme from that. With the multi-step Adams schemes, we have a slightly different perspective, where we're going to, instead of using the Taylor series, we're going to use polynomials of different order. So your family of polynomials are a line, a quadratic, a cubic. And it turns out the higher order polynomial you use can lead to a greater accuracy. Okay, so let's get started with that. So I'll get started with the multi-step methods now. The multi-step Adams methods. So what I'm going to do is actually just write down one of these multi-step methods so you get the idea of how it's used, and then we'll derive it. So turns out the second order Adams-Bashforth scheme uses values at steps n and n minus 1, and it looks like this. So xn plus 1 equals x of n plus delta t on 2 3 of f at step n minus f n minus 1. So f of n means f at step n, and f of n minus 1 means f of n minus 1. And you can already see that it already looks easier to evaluate, given assuming you have the value of f at n at n minus 1, easier to evaluate than Runge-Kutta, because Runge-Kutta had a step that kind of looked reminiscent to this, but it had all these other function evaluations beforehand. So the computational cost is looking less. And what we're doing then, as long as we keep track of the function at step n and the function at step n minus 1, we're evaluating the right hand side using that. And this is second order. So that means that this expansion, don't forget that we have to divide through by delta t to get xn plus 1 minus xn of delta t. We have an order delta t cubed term on here. So this is a very attractive scheme if you've got the ability of storing the function at previous steps. And I say it's derived based on polynomials. So AB2, second order Adams-Bashforth, is derived using a polynomial, e.g. line, quadratic, etc. In the case of AB2, in this case, we just use a line. So the line is a special case of polynomial. And then obviously if you want to go to hierarchy, you use a higher order polynomial instead. In this case, AB2, we use a line. So let's just write down the, see what we're doing. So dx by dt is f x comma t. Well, of course, when we're integrating this, when we're solving it as an ODE, we integrate, and we have x n plus 1 minus x of n equals going from tn to tn plus 1 dx by dt, which is then also equal to tn plus 1 tn f dt. I'm just going to drop the arguments in this case. So we approximate the contents of this integral. So what we're doing when we solve x and we're integrating f. And the key to these Adams-Bashforth methods is, rather than Taylor's expansion, which is what we do in Runge-Kutta, is we approximate this with a line. Okay. So this is where a diagram comes in, and this is just you can see the detailed line in the lecture notes. Yeah, I'm just going to draw it out because I feel that it sort of paces things. That's t, and we've got our time step, current time step, new time step, old time step, and obviously they're separated by delta t, which is your time step. And what we're saying is we've got the function, this is the function, we've got the function at step n, and we've got the function at step n minus 1. And when you've got two values, that's enough to construct a line. Obviously, you need three values to construct a quadratic, etc. So we can construct a line like this. Okay, and then we extrapolate using that line. So we're going to call this P of t. P for polynomial. In this case, it's straight line. And we're using the n minus 1, the n values to extrapolate further forward, and we know the time step. So that's all we need. And actually, if we have that, we can just write down the formula for P. P is, and I'm going to use I'm not going to use y equals mx plus c. I'm going to use a form of the line where you have the starting point of the line that you're given, which is fn minus 1, and the gradient. So the gradient is fn minus 1 over delta t. Yep, that's the gradient of that thing. And then we have this variable t, which can float between these discrete values, tn plus 1 times by t minus tn minus 1. So it's the first value times the gradient times the change from there. Okay, so all we need to do then is substitute that in for our expression for f. So if you see it, this is approximation. So, and then integrate. And that's how we get our scheme. And we substitute P for F on the right hand side. So we have xn plus 1 minus xn equals the integral from tn plus 1 on tn of f dt. And this is where the approximation comes in, the polynomial approximation, tn plus 1 tn p dt. And then from the previous board, we had the expression for P, it's f of n minus 1, f of n minus 1 delta t, t minus t of n minus 1 dt. Okay, so it's important to know what we're integrating and what we're considering fixed. So as far as this integral goes, the values of fn minus 1 and fn are fixed, and tn minus 1 is fixed, and delta t is just a constant. So the only variable in here is t. Yeah, and that's what we've got to vary. So this can be considered a constant, the integrating, this can be just constant coefficient. And we're integrating between, but it proves convenient actually to make the integral easier to solve. You could solve it like that, but we could do a substitute a dummy variable, which is just a substitute for t to make the integral easier. So we're going to call s, which is simply t minus n minus 1. Okay, and that implies we do the derivative of that, so that's ds. Obviously tn minus 1 is considered fixed, so ds equals dt. So what we're going to substitute in here is s, and we've got ds coming in here. The other thing we have to think about is the limits of this integral now will change with s. So remember that s is t minus tn minus 1, so that's tn plus 1 minus tn minus 1. And this one will be tn minus tn minus 1. So let's just write that out. now change it to this s variable, tn plus 1 minus tn minus 1. In fact, I'm going to write this on the new line. Tn plus 1 minus tn minus 1, tn minus tn minus 1. So those are limits now in terms of this s variable. You still have your same function there, and then you have your gradient, which is f of n minus f of n minus 1 on delta t s ds. Okay, so we've simplified this bit. Now it turns out that these limits are actually a lot simpler than they look. Remember, we're on a timeline. We've got tn there, tn plus 1 is there, tn minus 1 is there, and they're all separated by this thing called delta t, which is our time step. So it turns out that tn minus 1 will just equal to 2 delta t, say. Okay, and then tn minus tn1 will just be equal to delta t. So the integral becomes 2 delta t to delta t f of n minus 1 plus f of n minus f of n minus 1 delta t I should really put brackets around there to show that it's that's multiplying ds. So we've got a term here, essentially a constant, so that integrates to give it s. Here we've got s, so it becomes very easy to integrate now. It's just getting it in that form that's easy to use. So the integrand becomes f n minus 1 s plus f of n minus f of n minus 1 on delta t, and of course integral of s we've known from a long time, it's s squared on 2, and the limits are 2 delta t on delta t. This is xn plus 1 minus x of n equals. So all this is a consequence of using a straight line approximation to integrate the right hand side. So if we just now evaluate the limits, the first term gives a 2 delta t minus delta t in there, which is just simply f of n minus 1 times delta t. And then let's actually put these in brackets again. F of n minus f of n minus 1 on delta t, and so we've got a 2 delta t squared, which gives us 4 delta t squared minus 1 delta t squared, so that gives us a 3 delta t squared on 2. And then finally, just bringing together terms in f of n minus 1 and f of n. The term in f of n is simply delta t on 2, because those cancel 3 of f of n. Yeah. And then you've got 1 of f of n minus 1 minus 3 2, so you end up with minus a half f minus 1, so that you get minus f n minus 1, which is exactly the expression I wrote down in the first place. This is your AB2. Okay. So the recipe is to get the new value, take 3 of your function at step n, minus 1 of this step at n minus 1, multiply it by delta 2, and there you go. Okay, and I think I was just checking the time there. I think that's a good place to pause. Next time we'll do a worked example of this using the same function we use for the Runge-Kutta method, just to confirm that we're getting second order accuracy out of this. Okay, thank you.